Section 8-4, Testing Claims About a Mean. The main idea behind this section is to test a claim about a population mean. There are two parts to this. The first part, we will test a claim where the population standard deviation is not known. The second part discusses a procedure where we test the claim about a mean where the population standard deviation is known, but this does not happen very often. Part 1. Testing the claim about a mean when the population standard deviation is not known. We will use a t-test. We should be familiar with the notation. N is a sample size, x bar is a sample mean, and mu is a population mean. We also would have S, the sample standard deviation. Requirements, we want to make sure that the sample is simple and random, and we want to make sure that either the population is normally distributed or our sample size n is large enough, like greater than 30. The test statistic will be given by t is equal to x bar minus mu divided by s over square root of n. We've seen this before when we were first introduced to student t distribution. When we're running the test and we're interested in finding p-values, or we're looking for the critical values, we're going to need the degrees of freedom to be n minus 1. And just a quick look, I'm not going to read through it, but this is the set of properties that we've seen also back in Chapter 7 when we first got introduced to student t-distribution. Let's take a look at an example. Listed below are measurement radiation emissions in watts absorbed by tissue cells per kilograms of tissue. And they correspond to a sample of cell phones. So we want to use a 0.05 level of significance to test a claim that cell phones have a mean radiation level that is less than 1 watt per kilogram. Here we have a short list, but the summary statistics are what's important. We have the sample mean to be 0.938 and the sample standard deviation to be 0.423. A quick check of our requirements. We'll assume that the sample is simple and random. The sample size is n, and that's 11, which is quite small. So we want to make sure that this comes from a normally distributed population, and we can just assume that it is. So the first three steps is to establish the null and alternative hypothesis. The claim is that mu is less than 1 watt per kilogram. So the opposite of that is mu is bigger than or equal to. So remember that bigger than or equal to contains a condition of equality, so that the null hypothesis can be mu is equal to 1. And then the alternative hypothesis, mu is less than 1. So we have a 0.05 significance level, and we will be using a t-test for this. In our calculations, we get a t-test of negative 0.486. So if we compare that, our critical value that we would find would be negative 1.812. And this is a left tail test, so the whole shading goes on the left side. We notice that our test statistic is not in our critical region, so we will fail to reject the null hypothesis. We can also use the calculator to get our that same t-test statistic, but we also get a p-value of 0.319. Now 0.319 is clearly larger than alpha, the significance level of 0.05, so by the same reasoning we would fail to reject the null hypothesis. Because we fail to reject the null hypothesis, we can then conclude that there is not sufficient evidence to support the claim that the cell phones have a mean radiation level that is less than 1 watts per kilogram. Let's take a look at a slightly different example here. This time we'll assume that sigma is known. When sigma is known, we get to use the standard normal distribution. That's the normal distribution Z. But we want to make sure that you understand that this is extremely rare, and we can make assumptions about an unknown sigma and pretend that it's known, but in general, if we don't know it, we're going to use the t-test. So here we'll assume that sigma is known. So our test statistic in this case, we'll be using a z-test statistic. That's x bar minus mu is equal to sigma over square root of n. If we assume that sigma is equal to 0.48, then we can run through the test and come up with the same value. And if we come up with the same value, we'll see that our p-value for this is 0.3336. Now again, our p-value is large, so we're still going to fail to reject the null hypothesis, and we will come up with the same conclusion as before. Okay, that's the end of section 8-4.